Hello, folks. I would like to present the speaker, Heverton Augusto Pereira. Senior member IEEE, received the bachelor degree in electrical engineering from the Federal University of Viçosa in 2007. The master degree in electrical engineering from the University of Campinas, Brazil in 2009, and the PhD degree in electrical engineering from the Federal University of Minas Gerais, Brazil in 2015. In 2014, he was a visiting researcher with the Department of Energy Technology, Aalborg University, Aalborg, Dinamarca. In 2009, he was with the Department of Electrical Engineering, Federal University of Viçosa, where he is currently an associate professor. He is also editor-in-chief of... Opa, saiu aqui. Sorry. Editor-in-chief of Revista Eletrônica de Potência. His research interests include photovoltaic panels, grid-connected converters, and battery energy storage system.
Thank you for your kind presentation. So, good afternoon to everyone that's here today. It's a pleasure to visit Santa Maria. It's a very famous university in power electronics, and today is an honor for me to be here knowing more you during these days and enjoy Sepoc event. So maybe I talked with Rodrigo some minutes before, maybe the title adaptive control can be some trick, like maybe people can think about adaptive control like very complex techniques or very different techniques, but it's not my case. I will try to show some adaptations, adaptive things that we do in power electronics converters used in photovoltaic systems. Before I start, I like to show a figure about my university. I don't know if all of you know it. Viçosa is located in Minas Gerais. Is more or less 230 kilometers far away from Belo Horizonte. That's the capital. And this year we are completing 19 years old, the university, so almost 100 years there. And here is some pictures from there. It's a very beautiful place to go there. And maybe in 10 or 20 years, we will present a Sepoc there. Like now you are going for other place. So my focus is to improve our group, to have more members like here. Today we are not a lot of members, but I think that in some day we can be a Sepoc event there. So, and here is Giuseppe Laboratory. We start to work in this place last year. We was founded in 2010, and since there we start very small, very small. Because when I started working in Federal University of Viçosa, I didn't have a PhD yet. I was a master, but I started to think about this type of photovoltaic system because in 2010, you couldn't connect your system in the grid. It's not like today in Brazil, because the world's changing in 2012. And since there, we started doing about this. Like one day in Brazil, we can like have our own photovoltaic system, and so the day arrived 2 years later, and nowadays Brazil is one of the biggest players around the world about photovoltaic systems. And here I send Rodrigo, we have some social networks, like the LinkedIn, the Instagram, and also the YouTube channel. We have a lot of playlists where you can find some courses about power electronics, modeling control of photovoltaic system, modeling control of battery grid integrated systems, and short circuit and power flow. And also, I like to ask Rodrigo after to share with the linkage community from the event the link GTracer .gsep.com.br. We are like creating this platform where nowadays we have 3 modules. We have a Villalva optimization. Villalva was a researcher from Brazil that passed away last year, and he has a very famous method about how to estimate the parameters RS and RP of a PV panel. And with this model you can, and he had a MATLAB code where you can put the parameters of the panel, and you can find these parameters that you need to simulate a PV panel. And also you can download the Plex file. We have a agreement with Plex here in Brazil, so the university can download for free. Maybe if you don't have a formal agreement, you need to ask Plex, but they will give you a license to use in the university. So you can download the module or the simulation working. Also, we have another one that's a fit curve fit. So you can like put the PV panel in one condition and simulate, for example, in the standard test conditions. So you can take your data that you use in the lab, and also, if you like put some curves, you can do that. And the latter one, this one is the fit curve, is to, because generally when we measure, the points are not so beautiful. So if you like to put in an equation the PV modulus, so you can use that. And the other one that I told you that is to translate the data for other operational conditions. Okay. So I divide my presentation in some parts. So this one was the introduction that I did. And now I like to talk a bit more about the PV system and the power system. I took this picture from a website from United States where part of the system is very developed compared with us. And the most important thing that I like that you see in this picture is this part here. This one is the batteries. So, of course, in the middle of the day, they have a lot of production of energy based on PV panels, and they don't have load to spend all this energy. So they are saving this energy in batteries. Nowadays in Brazil, we don't have so many battery systems working. There is a lot of prototypes or some special cases, but it's not something that will happen like next year. But they are changing the rules, so I think that the next 5-10 years, we also will start to increase a lot the battery energy storage system in Brazil. And this one is a picture of my hometown city called São Miguel do Anta. And what I like that to show you is like very similar to Santa Maria. When we arrived by plane, we can see a lot of the roofs. And in the roofs, we can see a lot of PV panels. So maybe you cannot see all the PV panels there, but I call a special attention here. And when we come to Santa Maria by plane, we can see a lot of roofs with solar panels. What this means for us? Because general electrical engineer guys, they don't work with solar panels. They work with power electronics converters. But if you have a solar panel, this means that you have an inverter there. You have a power electronic device there. And this is in Santa Maria, is in my city, is in all the cities of Brazil, you can find a lot of solar panels. This means that we have a lot of power electronics converters spread around Brazil. And this is very good for us, because we can start to think about this. Like, this one is a very small PV inverter. Generally, a PV inverter can be like, if you talk about a small one, this may be 1.5 kilowatts, but the biggest one can arrive in hundreds of kilowatts. And also the most used in residential is around 5 kilowatts. So you can produce around 500 kilowatt hour of energy per month, and most of the families this is enough. And also this device working at very high frequency compared with the traditional power system, because our grid is 60 hertz, and the device is switching for 40 kilohertz. So this means a lot of things for us that I like to introduce here today, if you don't work in this topic. And the control generally work with a power factor equal to 1 or similar to 1, very close to 1. And this is the most important thing there. you have a power factor control, and you have an active power control that is controlling how much energy you can remove or you can extract from the PV panels. And inside this converter, I take an example of one small one that they have two stages, a DC-DC stage and a DC-AC stage. And inside this, there is the main characteristics, the MPPT, VDC control, protections, synchronizations. So all of the converters here in Santa Maria, you have a laboratory that can certify this type of tests. It's very amazing there. I went today with Professor Lucas there. And also, you can do another things. You can do harmonic compensation, reactive power control, active power control. Today, we cannot do active power control because most of the systems, they don't have a battery connected together with the inverter. But in the future, maybe in 5 years, most of them will start to have the opportunity to connect also a battery in the... Of course, there are many opportunities to buy this type of device, but it's not the most seller today. So I like to do a joke with you. If you don't work with power electronics, I will ask the guys here, please, to put a play here in the first music. So thank you for the first video. And now, like we have Professor Lucas that is a pianist, so he can listen very well. I don't know if all of you can play this, but this guy play. I cannot play what he did. So I'm not saying that he play bad. I cannot do what he do. I don't understand anything about music. And this work very well. You can listen to the music. You can see what song is. It's a very beautiful song. Okay, it's working. You can use this type of device to play songs. But like now I like to show you another device that also plays songs. So please put the second video.
Princípio.
So our sponsor.
Cuidados para casa, com até 60% off, tem na Black Friday do Mercado Livre.
It's the same song. I think that's okay. It's okay. Why I show these two songs for you? Both are playing the same song. So if you understand music, you know that all of these are frequencies. So the notes, they have frequencies. So if you like to play a song, you need to understand the frequencies. But the quality of the device can change the way that impact people. So when we have a power electronic device, we are talking about a very nice device. And which type of song we are playing today? So this is my type of, not like to say bad things about the power device today, because they do the job. They are doing very well. But I like to say that for the future, we can continue playing the same device, or we can change a bit the device and improve the song. So next slide, let me put here. So this one we did in our laboratory in GCEP. So if you can play, please.
Notícias de última hora.
Duracell dura mais, muito mais.
Okay. So we take a commercial power device from PHB Brazil, and we change the software of the device, and we are controlling like the current, 2 amps, 3 amps of fundamental, 4 amps. And now we start to put like a third harmonic. So we are asking the device to inject a third harmonic, increase this one. After we put fundamental plus third harmonic, increase the third harmonic, so you can see that the waveform is very bad now. Increase a bit more. So we change the frequency. We change the way that the device is playing. And we can do this. It's only change we didn't change anything in the converter. We only changed the software. So it's the same current sensor, it's the same voltage sensor, it's the same processor. And we changed the song that was playing there. Most of us, we cannot listen 60 hertz or 300 hertz, but it's a frequency. So let me show, can I? Okay, here. So, okay. So now let's go to the first case. So I like that to understand that you can change the converter. Because of this, the presentation title, I add the adaptive. It's not because of adaptive control technique, in the meaning of that I'm changing the control. I'm changing the way that the device will work. So the first thing that I like to show you is about improve the losses. So many people like to reduce the losses. And how we can do this? There is a lot of things. There are a lot of ways to do this. We can change like the hardware. We can change the hardware and the firmware. We can change only the firmware. So there is here some topology that you can try. What's the best one? So you can try the device, wide band gap device. You can change the modulation for a discontinuous modulation. Also, you can change some characteristics of the thermal conditions. And we are proposing the first part here. Why we cannot change the DC voltage of the converter? Because why you need a DC bus in the converter? Because you like to inject current in the grid, into the grid. But if the current is very small, for example, in the beginning of the day, you don't have a lot of sun here. So the current that you are injecting is very small. And in the beginning and in the end of the day, the current is very small. So why you cannot change the voltage reference? Why we would like to change the voltage reference? Because the switching losses are related with the voltage, DC voltage. So if you reduce the DC voltage, when you are switching, you are reducing the losses. So this was the strategy behind this. Here there is a small equations here to show the voltage that you are like to synthesize using the converter. Of course, that is impacted by the impedance of the grid, impedance of the output of the converter, and the grid voltage. So when the grid voltage, in the first case, the grid voltage is V0. And you need to synthesize Vs. If, for example, the grid voltage increase, this can happen and it's normal, for example, increase 10% in some conditions, at least in rural areas, is very common the voltage have variation during the day. So if the voltage increase of the grid, you also need to increase your synthesized voltage. In this situation, you need to increase your DC bus. This way, you need to look for the standards. What is the worst case? What is the not so? Because when the voltage of the grid is going down, it's better because you can reduce a little more the DC link. But you need to think if the voltage of the grid decrease, maybe you need to increase the current to keep the power. So it's not so straightforward to analyze this way. And here there is a lot of things. So basically there is the structure. Here is the modulation, the synchronization, very basic structure. And here is the modification, the adaptive control. So instead of I add a reference that is constant, I like to give a reference that I will show you equation 2.8 that is based on the grid conditions and in the grid current that I like to inject. Here there is other case that we create like a index called k, where k can be equal 1. So if k is equal 1, you are in the, let's say, traditional case. And if k is more than 1 or less than 1, you are doing one adaptive in the control. And here is the equation 2.8. I will not show how it's calculated, everything, but so you can see that depends of some parameters. Some of them are constant, like the frequency of the grid, the resistance and the inductance, they generally will not change, but the grid voltage and the current ID and IQ that you are injecting, this will change during the day. Okay, so this current are changed here during the day. Okay, so this was the first case. And we like to understand, okay, I can do this, it worked very well, but what is the impact in the lifetime of the converter? I will increase the lifetime, I will decrease the lifetime, because maybe the voltage can decrease here in the DC bus. But how the elements, at least the semiconductors and the capacitors, will feel this movement that I did. So we did a lot of tests. There is some methodologies. I don't like to say that this is like the, when we talk about lifetime, there is a lot of methodologies that you can be using and you can use during the study. So I will show you one of them. So we take the experimental setup based on PHB power electronic device. So here is inside the device, we have the capacitor, the inductors, and here we can see the power devices we cannot see because it's behind the board, the PCB. Okay. What is the bad thing about this device? Is this DSP? Because it's a very cheap DSP, because the industry like to save a lot of money, but it can do the job very well. But when we try to implement very complex strategy or very different strategy, sometimes you are limited by the software. In this case, it's a point-fixed DSP, so it's very complicated to do modifications. But our group, like, they did a very good job, and they could implement the equation that I show you here, and in real time we can calculate the voltage that I like to have in the DC bus, and I will control it. And here is a base case where in red we have the traditional one, and in blue we have our proposed strategy. How you can see, we did some modifications here. For example, we did a step of reactive power. Why I like to do this? Because I like to see how the control feels this. So here it's a small step, because it's controlling the fixed current, but here you can see that to inject reactive power in the system, I need a higher DC link. And if it is inductive, if it's capacitive, observe that the DC link can decrease a bit. So this will bring some ideas, because in the second case that I will show you, I will talk about reactive power. So this one was based thinking about the second case that I will show you. Because why I'm changing the reactive power? So because it's a possibility that we can do, and I will show you later. And here in the MPPT, you can see that change the strategy didn't change the way that the MPPT works. Okay? And here in the simulation, you can see the difference in the temperature of the IGBT and the diode. So only changing the reference of the DC link, you can reduce the temperature of the power electronics device. And you are saving energy when you do that. Other here, but for the boost IGBT, boost diode, and capacitors of the entrance and from the DC link. Here the modification is not so interesting, but in other case we can reduce a lot this temperature. The reliability study, the PV inverter lifetime are characterized mainly by the semiconductors and capacitors. So I will show you here a figure, a very traditional one, where what's the big failures that happen in a PV inverter? Are the power device and the capacitors. Of course that there is other important failures like gate drives, but in this study we didn't have a methodology to understand how the gate drives will fail. But for the capacitor and for the power device, there is a lot of methodology that can be used in this direction. I don't like to spend a lot of time how this is done. So there is some classical strategy that we need basically a mission profile. So the most important thing here to do this type of study, that you need a mission profile for temperature, ambient, the solar irradiance, and grid voltage. And also this means that if depends of the solar irradiance and the temperature in the environment, maybe the same result done for Rio Grande do Sul can be totally different from Minas Gerais. Maybe inside the state, in one place you can have one result, in other city you can have another different results. So it's not so easy to conclude based on reliability, but give you some ideas. Of course that if you improve here, you will improve also in other place, but maybe not in the same magnitude. So we create this type of power losses lookup tables, thermal model. We analyze long and short impact. Also, after we need to use a Monte Carlo simulation because inside the data sheet of the device, there is some parameters that can change 10%, 5%. So you can understand how this is done, looking for the data sheet, and they will give you some directions how much this power electronic device can change. And based on this, we can see the profile of current, or of temperature, in the IGBT, diode, DC link, everything. And concluding this first part, here is the conclusion. Our proposed strategy can increase the lifetime B10 from 18.1 to 29.4 years. This is a methodology that say that the B10 say that how many time will delay for 10% of the samples fail. Of course that we are not saying that the PV inverter will work for 29 years. This is not the, at least for me, I don't look for this number and I believe in this number because this is a comparison between two things. There is a lot of other things that were not inserted here, like the gate drives, other steps that we didn't add in this study. But the good thing in my way of thinking that you can see based on statistics, compare the both strategies with the same conditions, that using the proposed strategy, you can increase the lifetime of the power electronic device. Okay, so I finish here my first case. Now I like to show you the second case, that we use this inverter to produce or to have an ancillary service. This is a topic that is growing a lot nowadays because we can, like I showed you in the beginner, this device is very smart. So you can use it to do other things. And I will show in this next case the reactive power compensation. The first question is, why I like to do one ancillary service? For photovoltaic systems, I can answer you very easily. Because in general, in our case, for example, you have sun between 6 a.m. and 6 p.m. Maybe in 1 month or other, this can change a bit. This way, you have a power electronic device in your house or in the industry that it's in stand mode during approximately 70% of the time. Because in some parts of the day, you have a margin here of power that you are not using because there is enough sun. In this case, we take the total area of the square and remove the square of the irradiance, and this area here is around 33%. So you have almost 7% of available power that can be used for other things. So we choose the PV plant plus one industrial system. Why we choose this study case? Because, for example, for homes in Brazil, we don't pay for reactive power. You can take a lot of motors in your house with a power factor 0.8, and anyone care about that. But for the industry, they need to pay in the end of the month a quantity of the reactive power if it is below 0.92. And I like to show you other problems when you have a PV system. So here you have the industry with the generator, they have a lot of motors, and you add a PV system to decrease your bill, decrease your electricity bill. So many industries in Brazil did this. What they didn't know, because people didn't count for them, because many of the people that install PV systems didn't know about this. In industries, they have a lot of capacitor banks. Why they use capacitor banks? To correct the power factor. What's the problem of capacitor banks? That they have steps. So they have some quantities that are defined, and they switch the capacitor. And sometimes you cannot change this switch in a very fast way, maybe in minutes or seconds, but not in milliseconds. For sure, not in milliseconds. Maybe in minutes you can, because the switch will burn if you do this very many times during the day. Here is one example that I'm showing that we are taking the PV inverter from PHB, inject only active power, and now we like to inject also reactive power. You can see that, like, for example, in this part and this part is more, the average temperature here is 37 degrees, and here is 42. What does this mean? That if you like to do more things, there is a price. The price is in lifetime. In the first case, I show you that's possible to reduce the time or increase the time. But in this case, I'm saying for you, you need to pay a price. If you like to inject reactive power in the system, you need to pay a price. The price here we can see in temperature, but also we need to study, do a lifetime study to understand how many years I will reduce my system. And in terms of control, you are not doing a lot of modifications. You are working only here. All the control loops will be the same, the gains, but you are changing, like instead of, for example, I have 0 here, 0, I like to have 0 in the grid of reactive power. Or maybe in some cases, for the biggest inverters, maybe they need to answer, like if the voltage decrease, they need to increase the reactive power. So there is some low voltage, high true curves that they need to follow. At least wind turbines, this type of converter, they need to follow the reference of a low voltage, high true. But here, instead of have a 0 here, why I cannot have a reference? But you need to take care, because you need to inject the active power coming from the PV panels, and now you like to inject reactive power. But the inverter has a limit. So he cannot do what do you like. There is a limit that you need to respect, okay? And I like to show you a problem that many people don't know in Brazil, that in the industry that installed the PV system. Imagine the situation, only a hypothetical one, okay? You have your load, active power load here, 1 PU, and your motors in the industry, they are taking maybe 0.4 PU of active power. And you add a PV system. You add a PV system. When you add a PV system, what happens in the middle of the day? You are injecting current in the grid. But there is some special, because here, this area here is equal this area. Because of this, here is a bit more, 1.4. There is some special moments of the day that, for example, when this is equal 1 PU, here is equal 1 pu. What's the active power from the grid? 0. So if the active power from the grid is 0, and you have reactive power, only reactive power, what is your power factor? This is very complicated because you need to have a capacitor bank that is need to be able to compensate all this reactive power. Because in some moment it's 0, so you need to pay in the end of the month the bill. And more, because I like to show this curve. This is the energy that you need. Like I told you, in some moments of the day, you need to have the same quantity of reactive power in your capacitor bank. And in this moment, you are injecting a lot. And when we publish this paper about this topic, we call, because there is a very famous curve in the power system that they call of duck curve. And we call this one of catch curve. Because people say that if we put an eye here and the other eye here, can be a catch curve. So we call of catch curve. And here we can see like what is happening like when you have the installation of PV system. If you don't control your reactive power, if you don't have capacitor banks, you will start to pay a lot of reactive power in your bill. In our mind, why I cannot use the PV system to compensate also reactive power? So I can deliver for the customer 2 services. In the same converter, I can deliver active power and also reactive power. In this case, we can design a capacitor bank to have a very controlled power factor close the reference. But it is almost impossible to keep all the time, because in these moments, the variations of the sun are very fast. And you don't have a degradé in your power bank able to follow small modifications. So in some cases, even with a capacitor bank, you can have problems to control exactly the reference. Because we can see that this is like a discrete, let's say that this is a discrete operation. In the other side, with the power electronic device, you can have a continuous operation. If you like to put 1.1, you can put. If you like to put 1.2, you can put. And the other important thing, we are talking about 60 Hertz, because reactive power is 60 Hertz. So it's very easy for the converter that is switching 400 kilohertz to play a song that is 60 Hertz. It's not so difficult to do this. So we implement here, we have from supplier 2 power source. One is a PV emulator and the other one is a grid emulator. And we have here the converter. And here are the parameters of this converter. Look how this, if you don't know to work in this area, look how this is fast. In this moment here, 1 second, I asked for the reactive power go from 0 to 900 watts. Look the transient here. It's very, very fast. To a modification that is rude, because the inverter is 1.5 kilowatt. And I am asking almost more than 50% of variation. And this is very, very easy, almost no transient, and easy to do. And here, we start to think about, okay, how can we convince people to buy this idea? So instead of you buy a converter, for example, of 1.5 kilowatt, why you don't buy one converter of 1.8? You will not increase so much the converter. And I don't know if you know, but some companies, they sell a product, for example, of 2 kilowatts, and they have the similar product of 4 kilowatts. And they only change the software. It's like the oscilloscope. They say for you, do you like 100 megahertz? Is this price. If you like 200 megahertz, I can send you a key, and you put the key, and they start to work like 200 megahertz. I think that the same can be done with power device, because most of the company, they have similar products that they only change some software inside the device. And here we like to understand how much we need to oversize the converter. For example, if the converter is not oversized, of course that you can like do the job, but part of the time you don't have enough power, available apparent power to do this. But if you increase the apparent power in 20%, like you see in the red here, you can keep the power factor inside the limits during all the time. So this is the idea. You can like upgrade your converter and operate during with control of the reactive power. Based on this, we did a lifetime study where we take a profile, did a Monte Carlo simulation. So here is the mission profile of active power. We take this profile of a company that is working in Viçosa. It's only 1 week of mission profile, but we reproduce for all the year to have the complete mission profile. We didn't measure for 1 year. We only measure for 1 week, and we reproduce this. So for active and reactive, so we need the solar irradiance and ambient temperature. The energy that this industry spend is 558 kilowatt per day. We calculated based on this PV panel how is the production of this PV panel for Viçosa, and after we divide and found the number of panels that are necessary to produce the active power. And this is the active power produced by for this inverter. We have a tax here of 0.08 dollars per kilowatt hour. We have evaluated how the capacitor banks can solve this problem, and also for different power factors, and the PV inverter cost if we oversize the converter. Here are some details. I don't need to show this. I think that's okay. And here some case, like if I only add the PV panel in this industry, the bill will increase $8,253 per year, because I didn't compensate the excedent reactive power. And I also can like put a power bank, and part of the time, look here, more than 9% of the time, you are okay with capacitor bank. But sometimes it's not possible to control. So another solution, instead of designing a power bank for 0.92, why you don't design the power factor or capacitor bank for 0.93 or 96? So we see that if we design for 0.93, we can like keep the power factor almost during all the time. And here I show you like if I oversize the inverter, you can see that 20% of oversize is enough to reduce the number of hours that I am exceeding the power factor in almost zero. So this number of 20% is a very good number if you like to design your converter with a higher active power, apparent power. We also did the study of lifetime, consider the temperature. You can see that when you are injecting active and reactive power, part of the time your temperature increase. Here, you can see that you work around above 100 degrees Celsius. And here is the conclusion of this study. All the devices here, and we are analyzing like if I oversize the inverter, what happened? Okay, here we also analyze if I increase the C-link capacitor. So in this case, we are like change the capacitor, because we found that you can find some problems in the capacitor if it working in this way. It can be more hot. So we also propose some strategies that you are changing the capacitor. So you can increase the lifetime from 28.6 to 32.4 years, okay? if you like to change the IGBT, the traditional case is 74.5 amps, and if you like to put in the strategy, because this is the traditional case where you don't inject only active power. If I use the same case, my lifetime will decrease from 37 to 27. But if I increase the switch, the capacitance or the capacity of the current capacity of the switch, you can increase the lifetime of the converter. So there is a lot of modification that you can also do to improve the lifetime. Okay, so conclusions here, né? The power factor of one industry plant drops with the inclusion of PV system. Capacitor banks and multifunctional inverters can be used for correction. Capacitor banks advantage and drawbacks we show here, and also some drawbacks and advantage of PV inverters. I go now for the last case. Let me see here. I like to talk a bit more about harmonics, because when you talk about harmonics, you are increasing the frequencies. You are not in 60 Hertz. Here, also, all of these are one traditional strategy. What I like to include here, now I like that my converter, besides the fundamental current, I like that you also connect one additional current here. I will say you that to convince people talking about the harmonics is not so easy. With reactive power, we find a way because we can show for the industry that the bill will change. But when you talk for people that the motors will work better because you improve the harmonics, the THD, at least today, until today, I didn't find good arguments or good ideas how to convince people that are not from power electronics or power engineers that this is good. But I continue talking. We are using here a traditional resonant controller, okay? Any news here? And in this case, we did a strategy that we use a traditional structure to detect the fundamental components. So we measure the current of the industry or the current of the load. We pass for one PLL, but for the current, we can detect the fundamental component, 60 Hertz component, and we take the original signal with all the components and then remove from the original signal the 60 Hertz component that I detected. So here is only the garbage, let's say, because it starts from 2 to n. So the garbage is here. And we like to see if there is gold in the garbage. So we take this signal, we pass again in a harmonic detector. Because what is the most important thing? People look for THD. How the THD is calculated? It's based on the square, the current square, and you sum this. So if you like to reduce the THD, the best way is reduce the highest component. If you can remove the highest component, you will doing the best job possible. After, if you need to choose, you choose the second one, highest component. And this is the case. So we did some structure that I can show here. That how many stages do you like? I like to remove only 2, the first 2 most important components. This strategy, there is a limitation, because when we use this type of SOG adaptive control, there is an attenuation in other frequencies. So if I am here in, for example, 100 Hertz, my 108 Hertz, that is the third harmonic, my fifth harmonic is attenuated. So I'm not seeing the correct value. I'm seeing the value multiplied by this attenuation. What does this mean? That if the fifth harmonic increase, maybe if increase only a bit, I cannot see that now the fifth harmonic is the highest component. So there is this trick here. We implement this in Belo Horizonte, in UFMG. And here is the loads. We have a 3-phase rectifier that we work in sometimes like a 3-phase load. So we have here 5th and 7th components are the biggest one. And when we like to switch, we open here one phase and this come for a single phase load. So here you can see third, fifth, seventh. We can change the load during the tests to see if our component, we are compensate the highest component. Here is some case like I am in this condition and I change the load. So the fundamental increase, here is 60 Hertz, you can see, measured in the DSP. Here the fundamental, here is the, this is not the fundamental, this one is the highest harmonic, the number one, harmonic number one. That's not 60 Hertz, is the highest component. Is, in this case, is 300 Hertz, because my load is 3-phase, so here's the fifth harmonic. And when I change here, look that I go to load 2, the highest component is the third harmonic. So I can show you that in dynamic test, if the harmonic change, my detector can find the highest component. Here another test for the second highest component. We also can change this and can detect it. And here is the problem, because your load, your inverter current. So your inverter is sacrificing to have a very nice grid current. So you need to pay the price. You are paying the price here because this is the current of your inverter. But we cannot look for this like a bad thing. We need to look for like a piano that I showed you in the beginning. You are playing different songs. Your device you can do this. So if you take a piano and play only 60 Hertz, okay, you can do it. You buy the piano. But if you like to play the other notes, you can do a lot of beautiful songs. And this one is another with the other load, with more third harmonic. When you change for third harmonic, you can see that the current change the waveforms. And there is a detail here that I like to show you. Because I am asking to compensate one harmonic load. But in this case, my goal, first goal, is this headline. That is the fundamental. I cannot forget that my goal is to inject the current that is produced by the PV panels, 60 Hertz. And now I told you the inverter to inject also this harmonic current. But there is a saturation in the converter. This is the limit, in this case, is the limit of the current that I can inject. If I ask the inverter to inject this current, it will not do, because there is a saturation there. But if I put a saturation here, what is happening with the waveform? You start to produce harmonics in the waveform, because I did like a square wave. I cut the wave. In this way, you need to have some strategies here to reduce this for this. But how to reduce one harmonic in dynamic way? Because you almost need to take the wave that you like to inject and say, oh, I cannot inject all of this content because I have not capacity to do this. And we propose here in the Lucas PhD a strategy to detect, like a peak detector, how much harmonic I can inject. And here is one case. You enable the harmonic compensation here, so in this first moment you can compensate 100%. In this case, you start to have some 750 watt per meter square. In this case, you cannot now compensate all the harmonics because part of the current is being used by the fundamental component. And if you put a load here, observe that reduce a little more the capacity of compensate more harmonics. And when you increase the radiance for 1,000 watts per square meter, in this moment you can say, I cannot compensate anything in this moment. And after, when the radiance decrease, you can return for a condition that you can continue using 100% of the inverter. And here's the case where you can see by waveforms. You start here only fundamental component, increase the harmonic, it's okay. When you increase a bit more, okay, I am in the limit. Here in this moment, I arrive in the limit here. And my compensator start to work to avoid that I stay in this condition for a long time. And in some cycles, I come to a limited condition. And here also, because now decrease the irradiance so I can compensate more, come for a place that I am limited again to compensate the load. So I am compensating all the load and I am not saturating the converter. And here you can see some people like this type of figure to see that everything is like inside the cycle. And here you can see that before the saturation strategy, you are doing the job above the limits, and here you are limited inside the limits. So you are doing, respecting the limit that the converter was designed. To finish my presentation, I'd like to thank you all of you for your time. And conclude that, like in my case, I think that power electronics are a very powerful device. And we need to teach the other players about these capacities. Which players? Maybe you need to talk with the guys from the industry. Maybe you need to talk with guys from the certification or for the Brazilian government, because they don't know about this. Many electrical engineers don't know about this. And we need to be able to explain this. Like I told you, for reactive power, I think that I found some ways to talk. But harmonic is not so easy to talk. But in my mind, like many things change the world. Like, for example, I don't have Bitcoin, for example. But I know that they are decentralized. There are a lot of many computers around the world working, doing the job, processing information, and take decisions. In this way, why we need a centralized reactive power compensation? Why we need a centralized everything? The generation now is not centralized anymore. So the next step in my mind is the other services, like the reactive power, and in the future, the harmonic, if we start to have problems about that. Okay? So thank you so much. And now, if you like, I can talk a bit more about some specific points.
Thank you very much for your presentation, Professor Heverton. So now we can talk a little bit. Any question? Professor Lucas.
Congratulations, Professor Heverton. Very good presentation. The case too about the reactive power compensation, because the fee that's paid for low power factor is considers energy, and reactive energy divided by active energy, not power exactly. And does the power factor, when the utility company considers for this fee, consider also the harmonics or only fundamental components? Do you know?
That I know is only the fundamental component. They take a window of 50 minutes, and they do like the average. They don't take, maybe if you are like in 0.9 during maybe 1 second, it's almost impossible to pay something, because they take a window of 50 minutes and they do the average in this window of 50 minutes. So this means one measure, like per 15 minutes. So they don't consider harmonics in this case.
So harmonic compensation is not necessary for improving power factor?
No.
No, okay. Thank you.
I have like a more generic thing. I was just during your presentation, I just was wondering about different things. Was like quite didactic, quite good presentation. And basically nowadays we are talking about power electronics everywhere, and you are like showing us like different cases here. And I would like to get like your opinion about how can we use like these interfaces. We already have these interfaces to provide like different services, like for like different auxiliary services for like the or power system, for like distributions, like to improve like quality and so on. I don't know if you can talk about which kind of different things can you expect for the future.
I think that there are different scenarios. Like, for example, many people in Brazil, maybe not in Brazil, but in some countries like United States, recently they have a problem of a hurricane, this type of thing, that they lost the connection with the power system. So they need a system that is stable, is good, with power quality. So maybe in this case, why we cannot have a harmonic compensation inside a local microgrid that is activated only in special conditions? Because if you work only in special conditions, you will not decrease so much the lifetime of the converters. Maybe it's a special case, 2 days, 3 days. In my mind, all of this software are very easy to implement in the device. You don't need to change the measurements. Also are implemented. In my mind, is only how to convince the industry to put the service and maybe sell the service like one extra service. Like, do you like this? Okay, it's only software, it's not. And I didn't show here because of the time, but we also are working in one idea, because in this case, I'm looking for the current and I am compensating the current. We are also working a case where I look for the voltage. So in a grid, I look for the voltage, and I don't know where is the problem. I know that there is a harmonic in the grid voltage, and I start to ask the inverter to inject current components, trying to reduce the THD of the voltage. Because this case is very specific, like for an industry or for a place that you can measure the currents. But in case that you cannot do this, like in our house, maybe you don't like to put a measurement or current measurement in the entrance of your house. But you can look for the voltage, and you can see that there is loads in your grid that is polluting this grid, and you can ask the inverter to inject current components to decrease these harmonic components. In my mind, is the best way, like to convince people, is like to give them the possibility to choose. Like, do you like to choose? Maybe it's not so expensive I know, I like to choose this one. And in these special conditions, like I told you, of hurricane or other things that happen around the world, people will say, oh, this is very nice. In this condition, save my life, or save my family life, because I could have a stable power system with a PV and a battery working very nicely without any problem during 2 days, for example.
Thank you, Heverton.
Someone has any question more? Igor?
Firstly, congratulations for your presentation, Mr. Heverton. Thank you for being here in Santa Maria. It's a pleasure for your acceptance of the invitation. And as I'm used to do, it's not a technical question, but for people who doesn't know, you are also the editor-in-chief of the Brazilian Journal on Power Electronics, of Power Electronics. And we know that it's still an emergent journal, a national journal. So I'd like to ask if you want to enjoy this space to make to share with us the news of the journal and the opportunity for publications that you have. Okay, can you talk a little bit about it, please?
Thank you for your question. Because of the time, I didn't put here in the slides, but I have here some extra slides that I had here. And I like to show you like some news about the journal. first of all, about the revision time. Many people send journals for papers for journals, and maybe delay 3 months, 4 months. This year of 2024, we were able. I like to enjoy the opportunity to thank all of the editors, like Fernanda is editor here from Federal of Santa Maria, and for sure she called a lot of you to review papers there, and we were able to reduce the average review time for the first round for 34 days. Of course, some of the papers can take more time, others maybe 20 days, but I think that is a very good number, because if you can wait 1 month for a first review, it's a very nice timing in my mind. And also, this year we are like the record of not the acceptance, but the submissions in our system. We already received this year 92 papers, and we were able, because of this. I'm thanking the editors, the associate editor. Edvan is here also. Thank you so much. He is spreading our journal around Europe and the USA.
I didn't know it.
And we were able to reduce the review time, increasing a lot the number of papers. It's not because we don't have job, Edvan. Do you agree with me? We have a lot of job, and people are doing a very nice job. I like to thank all of the reviewers, the editors. Today, our editorial board and our associate editor, most of them are abroad Brazil. This is one of the topics that are required by the impact factor. So they call of geographic distribution of the editorial board, and from the associate editors, and from the reviewers, and from the authors. I like to share with you, we have a Sobra app LinkedIn. If I don't know if you follow the Sobra app LinkedIn, this month we were accepted in the DOAGE. DOAGE is the Director of Open Access Journal. This is like to show for the world that we are not a predator journal. We don't like to publish a lot of papers. We like to publish good papers. So this is a seal that we received, and with this seal we can apply for the impact factor, and from the Cielo also. They require this type of seal to show. And in my mind, that we are working to submit now next month for Cielo to get the acceptance. Maybe can take 6 or more months. And if we get inside Cielo, automatically we go to the impact factor like a collection that Cielo has inside the Web of Science. And also, of course, we are working parallel to go to Web of Science directly. But it takes a lot of time, and I like to thank you for if you don't know the journal, here is the link of the journal and the website. So we change everything this year. We move for our open journal system that is an international system used by many journals. This in the beginning of the year took a lot of time, because we have in Sobra app more than 800 papers published since 1996. So we complete next year. We will complete the edition number 30. This year we are in the 29. So next year we complete the edition number 30, and I'm very proud to together with my colleagues to try to do our best to improve our journal. For the researchers, they have a good place to publish with a fair price, because we also look for many journals around the world that are like you need to pay maybe 3,000 euros, $3,000 to publish. And this is not our philosophy. We like to, of course, that we need the money to pay the bills, let's say, but the price is very cheap compared to this. Like for Brazil is, if you are Sobra app member, until 8 pages is for free, and more than 8 pages is 250 reais per page. That is in dollars, 50 reais per page is nothing compared with other journals. So I think we need to keep it this low price and increase the quality of the journal. But this one, I need you, and I need all of you from Santa Maria that continue sending papers and supporting our journals. So thank you for your question.
Thank you very much. We knew that the impact factor has increased since last year, and thank you for all this data. I asked you before lunch, 10 minutes before lunch, about the information. I didn't know that you had so much organized data to share with us. Thank you very much.
Acho que eu vou falar em português, porque acho que essa questão da Sobraep, de certa forma, é um assunto de interesse nacional, digamos assim. Na verdade, muitas pessoas, assim, que eu sei que a questão da equipe ali, de edição e tudo mais, é um número, assim, limitado de pessoas, então as pessoas que geralmente submetem os papers para a revista não têm muita ideia do quanto de trabalho isso é custoso, assim. Então, eu que acompanhei de perto, só queria dar o depoimento, eu sei a quantia, eu tive assim, várias reuniões já com o Heverton em relação à questão de organização da revista, assim, então só queria, assim, na verdade, deixar até o agradecimento para o Heverton, porque a questão do que vocês estão vendo, assim, de melhorias e de modernização da revista, assim, 100% do trabalho do Heverton e da equipe dele, então eu acho que vai ser uma herança que você vai deixar para a nossa sociedade, a Sociedade Brasileira de Eletrônica de Potência, vai ser uma herança, assim, extremamente boa que você vai deixar para a sociedade, Heverton.
Quando eu li o currículo do professor Heverton, talvez não tenha ficado muito claro para todos, mas eu sei que muitos sabem, talvez outros não, mas o Heverton é o editor-chefe da revista Eletrônica de Potência. Eu sempre procuro orientar os meus alunos, alunos de TCC, mestrado, doutorado, a pesquisar os artigos publicados na revista Eletrônica de Potência, porque a gente tem lá a gente encontra um monte de artigos novos e antigos, clássicos, na área de eletrônica de potência e controle. Então, tem alguns alunos recentes agora de mestrado que estão desenvolvendo trabalhos, e eu estou sempre falando para eles, né, vamos submeter esse trabalho na revista Eletrônica de Potência, aí, porque é uma revista nossa, né, é uma revista nossa, mas a gente precisa ter cada vez mais publicações e também algumas conversas que a gente teve, né, nesses dias, incentivar mais contatos internacionais que a gente tem a publicarem também na revista Eletrônica de Potência, porque isso é muito importante para que a revista melhore os seus índices. Então, é muito comum. A UFSM é uma grande... os alunos, os professores da UFSM normalmente publicam bastante na revista, né, mas a gente também tem que tentar motivar os nossos contatos internacionais para fazer o mesmo, né? Senão vai ser uma revista só de âmbito mais nacional, e eu acredito que ela tem um grande potencial para se tornar uma revista com um índice de impacto cada vez maior. Professor Renes.
Primeiramente, parabenizar o Heverton e agradecer a aceite o convite a estar aqui junto conosco. E aí eu vou reforçar esse ponto histórico, né, da revista, que é muito importante a todos saberem que a Sobraep, desde a sua fundação, quer dizer, no momento da fundação nós não tínhamos revista. A revista foi criada após, se não me engano, a fundação em torno de 1990, 6 anos depois, a gente instituiu a revista da Sobraep, depois ela se tornou a revista de eletrônica de potência.
E o primeiro editor foi daqui, né?
Isso, então nós assumimos esse desafio, o professor Hélio que encabeçou, mas toda a equipe nossa deu, digamos, cobertura, né, e força para vencer aquilo que foi comentado aqui. Não é uma coisa simples. E é um trabalho voluntário dos sócios, né? Então, gratidão a todos os editores e a todas as equipes. A gente sabe que, junto com o editor, que é alguém que representa, mas tem uma equipe no seu entorno, normalmente normalmente o grupo desse editor que abraça essa causa, né? Os editores normalmente são líderes dentro de uma universidade, e é um trabalho que ele vem crescendo desde a origem, né? Então avançou muitos avanços, né? Só para vocês terem uma ideia, foi citado aqui, o que começou foi o professor Hélio, aqui da nossa universidade. depois veio, eu acho que foi o Alexandre Ferrari, veio o Pomilho, o professor Pomilho, que esteve aqui junto conosco, foi já editor. Depois houve uma pequena mudança, que se mantém até hoje, aonde o nosso o vice-presidente da sociedade assume a edição, não é isso? E esse vice-presidente vai ser o nosso futuro presidente da sociedade, e ele faz esse papel. Isso não foi na origem, surgiu essa regrinha depois, que é o único vice que eu conheço que trabalha muito mais que o presidente. A revista dá muito serviço, não é isso? Heverton comenta isso, que é uma característica da nossa sociedade. Normalmente os vices não fazem nada, é figurativo, é o presidente, a sua equipe, o corpo executivo, mas o nosso presidente realmente trabalha muito, tanto que às vezes quando o vice-presidente termina o período dele, né, que ele vai assumir a presidência da sociedade, é um alívio, às vezes até... enfim, mas é isso que a gente vê, um legado, cada vez mais a nossa revista está crescendo. E aí eu queria ressaltar o seguinte ponto, Santa Maria, porque nós iniciamos a revista, então tem essa relação histórica de afinidade com a revista e com a sociedade, né? Eu vi, rapidamente, parece que os artigos mais citados da revista são aqui de Santa Maria, tanto...
Só um detalhe, então, nesse trabalho que a gente iniciou, né, a gente detectou que a revista não estava indexada no Google Scholar. E o Google Scholar é uma das principais fontes de tráfego no mundo para as revistas. Então, antes mesmo de eu assumir, no começo desse ano, né, o Teles me deu a maior liberdade possível para poder já começar a atuar. Eu consegui novamente o login do Google Scholar, e na época estava assim, com 300 papers só, e a gente tem 800. Então, a gente fez um trabalho inicial de ter que cadastrar um por um, né, e fizemos uma revisão de todos também, porque a gente tem a nossa nova marca, né, fica até ali embaixo, Open Journal of Power Electronics. Antigamente tinha a marca Brazilian Journal of Power Electronics, mas essa marca ela era usada, mas não era oficial no DOI, né? Se entrasse lá no site do DOI, não estava escrito em lugar nenhum que era Brazilian Journal of Power Electronics. E aí, durante o último COBEP, muitas pessoas comentaram esse negócio de mudar o nome, né? E a revista, querendo ou não, desde o começo, ela é Open Journal. Nem existiam essas palavras na época, né? Eu acredito, né? E hoje o Open Journal é algo interessante, porque o paper fica disponível para quem quiser baixar, não precisa de pagar a taxa, não precisa, né? Para o leitor é de graça, né? E então, assim, eu falo, por que não nós, né, a sociedade que sempre foi Open Journal, usar essa expressão, né, sendo que muitos estão usufruindo dela hoje, porque nós também não podemos usar, né? Então, aí a gente oficializou, se entrar no site do DOI hoje, mundial, tem o nome, que o nome não pode ser mudado. Foi fundada como eletrônica de potência e a gente tem que continuar usar o nome para manter o ISSN. Então, não é possível mudar o nome da revista. Mas existe um tópico lá que chama Other Variation Title. E aí sim você pode ter um outro nome, no caso, para as revistas que não são em inglês, né? Então a gente fez esse cadastro, só que o Google Scholar só atualiza uma vez por ano. E agora, julho desse ano, atualizou o Google Scholar, a gente entrou novamente. Inicialmente, eles consideram só os 5 últimos anos, né? Então é um indicador que ele vai, é uma janela móvel, né? E dos 5 últimos anos, foram 7 artigos ranqueados com pelo menos 7 citações, né? Então é o jeito que eles ranqueiam. E, no caso, a gente até estava brincando aqui, tem um de Santa Maria aqui, né? Acho que tem 3 ou 4 dos 7 são aqui de Santa Maria, né? Tem mais citações, eu esqueci o nome, como é que chama o que tem um cabelo? Paulo, né? Estava brincando com o Paulo, ele tem 2, eu acho. Eu falei, o Paulo tem que ensinar para a gente, né, como evoluir. E ele deu algumas dicas do ResearchGate, como colocar no ResearchGate para poder ficar mais tempo visível para as pessoas. Depois até brinquei com ele, nós vamos fazer uma live para a gente ensinar, porque a gente tem que aprender, né? Ele descobriu maneiras de divulgar melhor o trabalho, né? E mais recentemente, nesse fundo também de divulgação, né? A gente está agora publicando todos os artigos também no LinkedIn também. LinkedIn é uma comunidade que tem crescido bastante. Quando eu comecei a publicar, a gente estava com 800 inscritos na sociedade lá, né? Agora a gente está com 1.300. Então, basicamente, a gente publica algumas notícias, webinars, mas a maioria das publicações é sobre revista, paper, né? Então, é uma maneira também de divulgar o nosso trabalho que a gente está publicando, né? E de quem escolher a nossa revista, né? Então, e fiquem à vontade, pessoal. Qualquer ideia que vocês tiverem de melhoria, fiquem à vontade de mandar para a gente lá, que a gente tem interesse em evoluir. A gente sabe que a gente é pequeno, a gente sabe que a gente tem que evoluir, e então isso é bom, porque a gente não está com o sapato alto, né? Tipo assim, ter tranquilidade que nós temos que evoluir. Para evoluir, nós temos que entender essas novas dinâmicas, né? Porque para a gente, que é uma revista pequena, é muito mais fácil a gente migrar para certas coisas do que, por exemplo, uma revista muito grande. Então, às vezes, algum de vocês começa a detectar movimentos, às vezes uma nova comunidade que está dando muita visualização, né? Mande para a gente lá, para a gente poder tentar fazer isso, né? E sair na frente dos concorrentes. Então, eu acho que esse que é o objetivo.
Heverton, eu tenho uma sugestão para ser pensada, refletida e melhorada. Nós tínhamos que pensar um mecanismo, porque publicar na revista é importante, tá, pessoal? Mas também é muito importante citação de artigos da nossa revista. Não vamos esperar que esse é um ponto importante, que as outras sociedades, que outros países, ou outros da Europa, da I3E, citem os nossos artigos. Então, portanto, nós tínhamos que criar, olha a sugestão, nós tínhamos que criar um mecanismo, normalmente com premiação ou com indicadores, dos artigos publicados na revista ou em outras revistas, os autores brasileiros, somente brasileiros, somente os sócios, vamos restringir os sócios, né? Fazer uma breve competição, pode ser competição, ou premiação, mais bonito que, né, fica mais, de que naquele ano esse pesquisador, esse autor, os coautores que mais, ou o autor que mais citou a nossa revista durante o ano, ou durante uma janela. Por que eu estou dizendo isso? Porque é uma cultura do brasileiro não reconhecer, isso é uma cultura nossa, tá? Não é um defeito e nem uma virtude. Nós não gostamos muito de citar conterrâneos.
Posso te dar um exemplo?
Pode.
Um exemplo clássico, pessoal, assim, para não falar de número, né? Nós temos, por exemplo, um paper do professor Vilalva, que até eu mostrei do coisa, sobre o modelo do painel fotovoltaico. Para quem não sabe, é um dos papers mais citados do mundo no I3E. Então, foi publicado no I3E Transaction alguma coisa, ele é um dos papers mais citados do mundo, tem mais de 1000 citações. E ele foi publicado primeiro na SobraEP. Então, nós temos um paper similar, que foi publicado na SobraEP. Então, assim, o que o professor está pedindo não é para a gente citar só por citar. Você tem que citar porque você leu aquilo ali e gostou. Né? Então, quer dizer, você tem dois papers muito parecidos. Por que não dar preferência para um em relação ao outro? Porque não dá para citar tudo também no artigo, você tem que escolher algumas referências, né? Então, acho que nesse sentido, com certeza, é muito bem-vindo. Né? Acho que já estou passando.
Eu tenho que fazer um destaque, eu estou falando aqui com o Rodrigo me mostrou, eu já tinha conhecimento disso, o professor Rodrigo, o professor Hilton e o Evaldo, o Paulo estão, nesse ranqueamento que a SobraEP fez, eles estão no topo. Um com 34 citações e outro artigo, que é o primeiro trabalho, e o outro com 12. Então, eu aproveito a oportunidade para parabenizar aí o Paulo, o professor Hilton e o professor Rodrigo.
Está marcado, né, Paulo? A live lá vai estar marcado, né,
por
você
essa
ensinar para a gente.
Por essa conquista importante que Santa Maria obteve, né? E é um orgulho tê-los aí, não só organizando o evento, mas produzindo ciência para a nossa sociedade. Parabéns a todos. Né?
Bom, nós temos um tempinho, eu até gostaria de aproveitar que o professor Reines comentou desse ranqueamento que foi feito dos artigos mais citados da revista da SobraEP nos últimos 5 anos, né? Então, esses 2 artigos surgiram da tese de doutorado do Paulo. Eu conheci o Paulo em 2018, quando ele começou a fazer a disciplina de controle adaptativo comigo, né? Daí ele gostou muito de controle adaptativo, quis estudar, e a gente começou a estudar, eu comecei a ajudar ele. E no início até foi difícil a gente começar a publicar, né? Foram muitas rejeições, a gente mandava. No início foi bem frustrante, eu lembro do Paulo me ligando, o que está acontecendo, a gente não está conseguindo publicar, até que a gente corrigiu algumas arestas, fez algumas lapidações e começaram a sair os trabalhos, né, os nossos artigos científicos. E esses 2 artigos que estão no top 2, né, dessa lista, surgiram a partir daquele trabalho, aquele grande trabalho árduo que a gente fez, né, com o professor Hilton, o Paulo, durante o doutorado dele, né. Então, é um grande orgulho para nós e a gente gostaria de orientar, né, de sugerir para os nossos colegas, alunos, professores, que também publiquem. E também é muito comum haver essa frustração de mandar um artigo e não ser aceito, mas isso faz parte do aprendizado. Se você sempre manda os artigos e é sempre aceito, você nem precisa melhorar, né? Já está perfeito. Então, às vezes as rejeições, elas são naturais e elas surgem para que a gente melhore o trabalho, para que a gente fique mais competente e consiga ter bons frutos, né? Então, só gostaria de fazer esse agradecimento. Pessoal, então chegamos às 3 horas, né? Vamos dar uma salva de palmas para o Heverton. E a gente gostaria também de presentear o Heverton com uma pequena lembrança do Sepoc 2024.